So let's now look at some of the maths behind this. Now, this, like so many other things in physics, is actually just a restatement of the principle of conservation of energy. If you understand that you don't ever make any new energy and that energy into something equals the energy out of it, maybe not in the form you'd expected, but the energy in equals energy out, that's what we're going to be doing in this short video here. Okay, so let's just recap some ideas. We said that a photon is a light particle. We will discuss about why the wave model doesn't work in a moment, but for now, a photon is a light particle. A better name, or rather a more descriptive name, is a packet of energy, okay? And so when you turn on the light, you're getting billions of these packets of energy, okay, flying around. Now, the energy of a photon is given, the energy of an individual of one photon is given by Planck's constant times the frequency of that light. Okay, so if you're getting some red light with a certain frequency, each photon has an energy E equals h times that frequency of the red light. If it's blue light, whatever the frequency is, E equals h times that for an individual photon. Now, it's really important to remember in this that we're dealing with a kind of a one-on-one effect. So one photon comes in and it frees one electron. So it's individual packets freeing individual electrons. Now, what we said last time was that there's some choices for this energy, didn't we? We said that the energy could be lower than the work function and nothing happens. Okay, no photoelectric effect. We said that the energy could be equal to the work function, and we said the electron is just about freed. And we started to call this the threshold. Okay, this is when the photoelectric effect, the electrons being freed, just begins to happen. If we say that the energy was greater than the work function, then not only is the electron freed, but it has kinetic energy as well. Okay, so it can go about on its way after it's been freed. Now, what I want to do now then, instead of writing E every time, because I know that E equals HF, I'm going to write these in terms of HF. So these are the possible scenarios. If HF is less than phi, no photoelectric effect. That means photoelectric effect, not potential energy. Okay, I should be clear on that. Then we can say if HF equals phi, the electron is just about freed. And if it's greater, then it's freed and got some kinetic energy. So we said that this bit was the threshold one. So what we do is, if you look, H is common to each of these. So what we do is this special frequency here, this special frequency is often referred to as F0, and F0 is known as the threshold frequency. Now, please note that for any metal, each metals, they all have their own different work function. So the energy you need to free it, the threshold frequency that you need to just about free it varies, okay, for each metal. And we'll look into how we can figure that out in a bit. So let's just write something out, principle of conservation of energy. Look, we know that the energy of the photon that went in must equal the work function plus any kinetic energy that the electron had if it was freed. All right. So principle of conservation of energy, when energy came in and energy came out. Okay. Now we know that E equals HF. We could write this, couldn't we? HF equals phi plus EK. So that's another way to write it. It's exactly the same equation. You could write it like this. Look, how's about this? HF equals HF0 plus EK. Now, if you think about that, because we've said that HF0 is the threshold frequency when it just about equals the work function, HF0. So instead of writing the work function, I can just write HF0. And you can keep going with this, can't you? So you can have HF equals HF0. Now you may remember that the energy a charge has is equal to its charge multiplied by its potential energy. Now the charge of an electron is always small e, and the potential we can write as V. So you may write it like this as well. This is quite a sophisticated way of writing it. If you really go into this, this V that I'm talking about there is often has a little s next to it, okay, and is referred to as the stopping voltage, and we'll get to that in another video. The point of this one is that the principle of conservation of energy is alive and well, okay? principle of conservation of energy. In other words, the energy of the photon went in, and that energy came out either as the work function, if it just about freed it, maybe it wasn't enough to free the work function, it lifted the electron up, the electron fell back down again. Or maybe if it was more than the work function, it was enough to free it and give it some kinetic energy. And you can express that, like I say, in any number of equations and combinations like this. Have a look in your data booklet and see how they express it. Okay.